and you've touched things that are hot, you've touched things that are cold, you know what that feels like. But when two objects have the same temperature, you could just say they have the same temperature. Or a fancier way of saying that is they are in thermal equilibrium. So being in thermal equilibrium means that they have the same temperature. All right? So temperature is a measure of how hot or cold something is, and two systems, or two objects are said to be in thermal equilibrium. So what does that mean when they are in thermal equilibrium? When they have the same temperature. So that's just an expression there that's quite one used. Okay, and then there is this law of thermodynamics that, zeroth law of thermodynamics. Why would they call it the zeroth law of thermodynamics? Maybe because it's, I don't know, it may be too obvious. But it's a zeroth law of thermodynamics, and it's stated over here. But basically what it says is the following. It says that if this marker is at the same temperature as this marker, so if these two are at the same temperature, and this marker is at the same temperature as this marker, then these two have the same temperature. It's almost an insult, right? They have the same temperature, and these two have the same temperature, therefore these two must have the same temperature. That's what it's called, the zeroth law of thermodynamics. And so here it's phrased in using the language of thermal equilibrium. So if objects A and B are in thermal equilibrium with, like if A and B are in thermal equilibrium with object C, then these two are in thermal equilibrium with one another. All it means is that if these two have the same temperature and these two have the same temperature, then these two have the same temperature, without making it complicated. That's really what it says. So anyway, it's called the zeroth law of thermodynamics. Okay, what is the instrument that's used to measure temperature? Well, thermometers, right? Thermometers are used to measure temperature, and what are some widely used temperature scales? Fahrenheit, the Fahrenheit scale, which we use here in the United States. If you watch the weather report and they tell you something about how hot it's going to be today, tomorrow, this week, they'll give you numbers in degrees Fahrenheit. But in just about every other country outside of the United States, any other country, the temperature scale that they use is the one in Celsius. But the unit of temperature in the metric system is neither of these. It's the Kelvin scale. So, there are various units for distances, right? You can measure distances in meters, in inches, in centimeters, in kilometers, in miles. But the unit of distance in the metric system is the meter, right? There are various units of time. You can measure time in units of seconds, days, hours, minutes, years. But the unit of time in the metric system is the second. So there are various units to measure temperature. You can measure temperature in degrees Fahrenheit, in degrees Celsius, or in Kelvin. Well, the unit of temperature in the metric system is the Kelvin. Okay, so if you're solving a problem and you need to get a numerical answer, and you plug in numbers, or you have to plug in a number for a temperature, you must remember to use to plug in the value for the temperature in Kelvin. It may be that the problem is given to you so that the temperature is in water in degrees Celsius or in degrees Fahrenheit. So if you want to, in many problems, you'll just have to be careful and then convert to the Kelvin scale and then use the value for the temperature in Kelvin. And I said in many problems, because I'm going to come back to that. There's a reason why I said that. So there are three temperature scales over here in this picture, in this column. So this is in Kelvin, in Celsius, in Fahrenheit. So, for example, suppose, I ask you, what is the temperature at which pure ice melts or water freezes? At what temperature does water freeze? And if the pressure acting on that ice is normal atmospheric pressure, like 1 atmosphere, the ice will freeze at 0 degrees Celsius. Now, 0 degrees Celsius is how many degrees Fahrenheit? Well, it's 32 degrees Fahrenheit. But what is it in the Kelvin scale? Well, it turns out to be 273. So ice melts and water freezes under a condition of a pressure of 1 atmosphere at 273 Kelvin, 0 degrees Celsius, or 32 degrees Fahrenheit. And by the way, usually when reporting the temperatures in the Celsius or Fahrenheit scale, you use the word degrees, like 0 degrees Celsius, 32 degrees Fahrenheit. But you don't say 273 degrees Kelvin. It's just 273 Kelvin. You don't use the word degrees. So you'll notice that, when you read the book, or if you write a report, right? Then it's just 273 Kelvin, 0 degrees Celsius, 32 degrees Fahrenheit. Notice the symbol for degrees, but not over there for Kelvin. So that's just a little note over there. Although you'll hear a lot of people say, 273 degrees Kelvin, and you know what they mean, right? But it's just that it's not how it's supposed to be said. Not that it matters, but Now, in that scale, in the 3 different scales, Kelvin, Celsius, Fahrenheit, if I ask you, at what temperature, though, does water boil? Pure water, with a pressure of 1 atmosphere. Well, the answer is that water boils at a temperature of 100 degrees Celsius, or 212 degrees Fahrenheit, or in this other unit of temperature at 373 Kelvin. Okay? And there's something to be noticed over here, which is the reason why I put up this figure here. How many degrees are there between water freezing and water boiling in the Celsius scale? This gap is how many degrees?
100.
100. So that if I were to increase the temperature of water from its freezing temperature to its boiling temperature at a pressure of 1 atmosphere, then you have 100 degrees in here. What about in the Kelvin scale? How many degrees are there
100.
in the Kelvin scale?
100.
Also 100. But that's not the case in the Fahrenheit scale. How many degrees are there between water freezing and water boiling in the Fahrenheit scale? 180. So the message is the following. A change in temperature in the Kelvin scale is the same as a change in temperature in the Celsius scale, but not the same in the Fahrenheit scale. And I say this because, and this goes back to that comment where I said in many problems you should use the temperature in Kelvin. We will write down some formulas in this chapter and subsequent chapters, like Q equals mc delta T. We'll write change in volume equals the initial volume made at delta T. But we will also write formulas like this. The intensity is area E sigma T to the 4th. Right? So whatever these quantities mean, that's not the point right now. The point is that if all I need in a formula is a change in temperature, all I need is the difference between the final temperature and the initial temperature, for example, that change in temperature is the same if I use the Celsius scale or the Kelvin scale. This is why you don't always have to convert from Celsius to Kelvin. Because, suppose you have water at 0 degrees Celsius, right, at the freezing point. And you raise the temperature by 10 degrees Celsius. So you raise it to what? To 10 degrees Celsius. So the delta T is 10. Now, what if you use another temperature scale like the Kelvin scale? Well, if it's at the freezing temperature, the temperature is going to be 273 Kelvin. And if I raise it to 10 degrees Celsius, that would be 283 Kelvin. The delta T is still 10. So for problems like that, where I'm using a formula, and what I need in the formula is that, the temperature, just one temperature, but all I need is the change in temperature, then I don't need to waste time. If I'm given the temperature in degrees Celsius, I don't need to convert the initial temperature from degrees Celsius to Kelvin and the final temperature from degrees Celsius to Kelvin, and then take the change in temperature because I'm going to get the same difference. So it saves time if you know that changes in the Kelvin scale are equivalent to changes in the Celsius scale. Now, if the initial temperature of the object is given to you in degrees Fahrenheit and the final temperature is given to you in degrees Fahrenheit, the delta T in the Fahrenheit scale is not the same as the delta T in the Kelvin scale. So in that case, you'll have to convert. But formulas like this, what about formulas like this? We will also talk about like an ideal gas law type of formula like this, PV equals nRT, for example. Formulas like this or that, notice that I don't have in here a change in temperature. What I have in here is the temperature. And because this is the temperature, so the pressure must be in units of pressure in the metric system, pascals. The volume must be in units of volumes in the metric system in cubic meters, right? And then this temperature would have to be in Kelvin. It has to be in Kelvin. And sometimes, there are tricky questions. Like they'll tell you, suppose you consider oxygen, and the temperature of this oxygen gas is 0 degrees Celsius, and then what's the pressure, blah, 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 blah. You say, 0 degrees Celsius. And if you put in 0 over here, you'll say, the pressure is 0. And that's wrong. So if the formula that you're using is such that it only make, what you need is the temperature, right, at a particular state, then in that case, you must convert to Kelvin and use the value in Kelvin. Not in Fahrenheit, degrees Fahrenheit, or not in degrees Celsius. Okay, that's just an important point. And let me just show you some of these formulas. For example, right in this formula here, you have a delta T. You can get away with using the initial and final temperatures in degrees Celsius. No need to convert. What about that one? There's another delta T. I don't care. I don't need to convert to Kelvin from Celsius if I'm given the temperature in degrees Celsius. Let's see, blah, blah, blah. Blah, blah, blah. That's a delta T. Delta T, no need to convert. Delta T, no need to convert. That's a delta T, no need to convert. Well, that's a T by itself. There, I need the temperature in Kelvin. This, what about here? What do you think? Should you convert or not convert?
Convert. Oh wait, no.
Convert?
No.
Is, in other words, the question is this, is T final to the fourth minus T initial to the fourth, is that the same as T final minus T initial to the fourth? No. So therefore you must convert to Kelvin. You must. Okay? So, okay, so that's that, blah, blah, blah. What about in the next chapter? Let's see. How about here? Let's see what's up in this chapter. And this is a very important point, so it saves time, in an exam, in a quiz. Why do you need to convert? Why do you not need that has to be clear here. So in this formula, let's see. See this temperature right there? It's by itself. You need to convert it to Kelvin if it's given to you in whatever, in Fahrenheit or Celsius. You must convert it to, because this is not a delta T. You see that T right there by itself? Okay? So what about that one? See, T by itself, you must convert to Kelvin. See that T by itself, must convert to Kelvin, must convert to Kelvin. But this is a delta T, no need to convert. Delta T, no need to convert. And so on. So there's a lot of this. So I just want you to be aware of that. Okay, so we're good over there, right? Also, another point that I want to mention is this. So this is the T sub F. You use F as a subscript. That's the temperature in the Fahrenheit scale. T sub C is the temperature in the Celsius scale. But then T by itself with no subscript, you don't put a T sub K for Kelvin. It's just T by itself. That means in Kelvin. And this temperature, when referring to the temperature in Kelvin, that's called the absolute temperature. So if I ask you, what is the absolute temperature of this marker? I'm asking you, what's the temperature in Kelvin? I mean, I could ask you, what is the temperature in Kelvin? Or I can ask you a different question, but it's really the same question. I can ask you, what is the absolute temperature of this object? If I use the word absolute temperature, it refers to the Kelvin. It's the temperature in the Kelvin scale. And something interesting about this diagram, this table that I have there, figure, whatever you want to call it, is the following. Okay? Another very important point. Notice that, again, you have the Kelvin scale, the Celsius scale, and the Fahrenheit scale, right? And I just chose this point over here. You know, what temperature does water freeze? 273 Kelvin, 0 degrees Celsius, 32 degrees Fahrenheit. All right, now, what happens if you make the object colder, 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 colder? So the temperature gets smaller, 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 smaller. What I like about this picture is that this over here is the lowest possible temperature. So, what is the lowest allowed by nature? What is the lowest temperature that anything, I don't care what it is, that anything can get cooled down to in degrees Celsius? It's minus 273 degrees Celsius. What about in degrees Fahrenheit? I tend to see this as minus 459, but maybe they round it off to minus 460. And in Kelvin, what is the lowest possible temperature? What is the corresponding temperature value in the Kelvin scale, the absolute temperature value, when the temperature in the Fahrenheit scale is minus 460, minus 273 in the Celsius scale? It's 0. And that's the lowest possible temperature. So if anybody tells you the temperature of this thing is minus 5 Kelvin, it's wrong.
Is that actually physically possible for something to have a temperature that low, or is that just a theoretical limit?
So Kelvin is the limit, but people have managed to cool down using, you know, special equipment and special techniques to like 10 to the minus 10 Kelvin, but it's still positive. It's just 0.0000 and then a 1. So you know, so they keep getting it colder, 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 but still above 1.
Never reach absolute 0.
Right, and definitely not below 0. So it's like you're approaching, like one of those functions that are pushing, you know, just. So, you know, with fancy equipment, very expensive equipment, and various techniques and so on, you know, you can actually Google it, you know, what's the lowest temperature anything has been cooled down to, and using this, like, techniques, and, you know. So, now, according to theory, the current theory, that's the limit. what if all of a sudden someone manages to measure a temperature that's lower than that, and it gets verified? That should be a Nobel Prize in physics right away, right? And that means that the theory is incomplete, and the theory has to be rewritten. And that's the way science works, right? Sometimes you say, oh, this is it, that's impossible, blah, blah, blah. And then, whoop, somebody comes up with an amazing discovery that, oh, okay, it's shaking the grounds of physics. Okay, we have to, look at this theory and make, corrections to it. And, so there are experiments that drive theoretical work. And there are theoretical calculations that drive experiments. Like someone says, oh, you claim that the lowest possible temperature is just 0. Okay, let me do an experiment. Let's see if I can break that or reach it. And what if they do? But so far it hasn't been done. Yeah. And the second law of thermodynamics is involved with that, and there's some, there are various arguments that lead to that. So if somebody tells you, oh man, I'm gonna sell you this thing, and this thing is really cold. It's at like minus 300 degrees Celsius. Then, like the temperature of outer space, vacuum, outer space, is 2.7 Kelvin. So not even, so it's not even 0. But I say this because, right, what happens, see, the temperature of an object, right, at the very beginning I wrote it's a measure of how hot or something is, right? Like you can touch it, oh, it's hot, or you touch it, oh, it's cold, right? But it's related, using statistical mechanics, you can show that it is related to the average translational motion and jiggling of the atoms that make up the system, and the molecules and so on. So, for example, if you have ice, right? You have ice crystallizes in a hexagonal pattern. Water freezes and crystallizes in this hexagonal pattern. So you have a water molecule like this. That's a Mickey Mouse face. HHO. So H2O. A Mickey Mouse face is just this, pretty much the shape of a water molecule. So this is hydrogen bonds with oxygen. Okay. So when water freezes and turns into ice, it crystallizes into these hexagonal patterns. And maybe it's like that. I'm not being careful as to where I put the hydrogen. I'll just put them like that. So that's what, 1, 2, 3, 4, 5. Ooh, I need another one. So 1, 2, 3, 4, 5, 6. So 6. And then you have like a void over here. And then this too, you can have this. So let's see, that's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And you got another void over here. And I'll just do one more. 1, 2, 3, 4, 5, 6. And you got a void here. Right, so this is ice. And now, two things. One is that this hexagonal structure, 1, 2, 3, 4, 5, 6, they're not all in a plane. It's really in 3 dimensions. So some of these are really sticking out and so on. It's just that, I'm riding on a plane, right? So that's one comment, right? The other thing is that don't get the impression that these molecules are just like a statue. No, they're jiggling. As you lower the temperature, as they jiggle with a certain amplitude, right? Like the oscillatory motion that you learned about, like in Phys 185. So they're jiggling about their equilibrium positions. As you lower the temperature, they jiggle but less vigorously, with smaller amplitudes, and smaller amplitudes as you get colder. Now, a lot of people say that when the substance reaches 0 Kelvin, an absolute temperature of 0, they stop jiggling, and that's wrong. Atoms never ever stop jiggling. So when this thing reaches 0 Kelvin, or minus 273 degrees Celsius, they still jiggle. It's just that they don't jiggle as much as at any other temperature. but they don't stop ever moving. And I say this because, sometimes I've heard people define the absolute zero temperature as the temperature at which molecular motion stops. Molecules don't ever, atoms don't ever, they are in perpetual motion. They never stop. I mean, they could be coming this way and collide with another molecule, stop, and then go the other way, but overall, they just don't stop. As you raise the temperature of this unit over here, right? But before I do that, I have that statement over there. One is, remember, the absolute temperature is the temperature in Kelvin, right? So, absolute zero means, it's when the temperature is 0 Kelvin, because it's absolute. That means Kelvin, 0. It's when the temperature is 0 Kelvin, right? And that's when the system, let's say this ice, is in a state, in a particular situation where it has minimum but finite, not 0, right? Not 0. Minimum atomic motion. So the atoms are still moving. It's just that it's a minimum, but not 0. Because sometimes people think minimum is 0, but they're still jiggling. It's the point, right? But compared to the motion of these molecules at higher temperatures, at 0 Kelvin, they jiggle the least. But they still jiggle, is my point. So, minimum but finite, not minimum and 0. Minimum but above, finite. And when the system is in that particular state, in that situation where the temperature, the absolute temperature is 0 Kelvin, there's still jiggle, right? There is energy associated with that jiggling motion. There is still energy associated with, there are electrical potential energies between them, right? And so that's a state when the system has what's called the 0 point energy. So the 0 point energy is the energy of the system when it is at the absolute 0 temperature, when the temperature is 0 Kelvin. 0 point energy. It's the energy that the system has when it is at a temperature of absolute 0. It's just, I want to impress on you the fact that even at 0 Kelvin, they still jiggle. Molecular motion does not stop. They still jiggle. So it's minimum and finite, not minimum and 0. Okay, so what would happen if I put some, let's say this is a 0 Kelvin. They're still jiggling, right? And I start some fire over here and I transfer thermal energy to it. Then they're going to start jiggling more vigorously as the temperature goes up. And, I keep raising the temperature of the ice, 0 Kelvin, let's say, right? And then, or close to 0 Kelvin, and then 1 Kelvin, 2 Kelvin, 3 Kelvin, 4 Kelvin. What happens when this reaches 273 Kelvin, which is 0 degrees Celsius?
Like their bonds break?
Exactly. That energy that I add will then end up breaking this, break, the bonds break, and then the whole thing crumbles. And when it crumbles, you just have a whole bunch of Mickey Mouse faces, pretty much next to one another, right? And this thing can flow. And that's water. And this is the reason why the density of water is, well, you tell me, which of these two substances has a higher density? The ice or the water?
Water.
The water, because you have the same mass, right? You didn't destroy any molecules, you just broke the bonds between them. You have the same mass, but occupying a smaller volume. You don't have those voids anymore like you do over here. So this is higher density. And this is why when you throw ice on water, remember physics 185, right? Archimedes' principle and buoyancy and so on, the less dense object will float on the denser object. So ice floats on water, right? So this is higher density. And this is, it's a liquid, right? And this is a solid, right? And this is less dense. Now, not many substances actually have this behavior where, at the freezing point, right, the solid phase, the solid state is less dense than not all substances, right? I think the only other exception, I mean, there may be others, but diamond is one of those. It's just that it's hard to, to liquefy diamond. You need huge pressures, and so but a chunk of iron would float on iron. I'm sorry, diamond. I think I said iron, right? No, it's diamond. Sorry, I misspoke. Okay, diamond. So diamond floats. Diamond in its solid form will float in diamond in its liquid form. That's the only other substance that I know of, but there may be others. I don't remember them. Okay. So and then what would happen if when all of it crumbles, right? You break all the bonds, and you have water at 0 degrees Celsius, and then you keep adding energy. Then the temperature of this water is going to go up from 0 to 1 degree Celsius, right? That will be 274 Kelvin, 275 Kelvin, and go up until this thing reaches 100 degrees Celsius. And again, the pressure is 1 atmosphere, right? So what happens if you keep adding energy when the temperature of this water is 100 degrees Celsius?
It's separated enough to just evaporate.
Exactly. Then they really begin to separate. Right? It's not like you're breaking the bonds, but they just separate and then they move faster, so it becomes a gas, right? It boils. It turns into steam.